Hi everyone, my name is James Young, and today I'm going to be discussing the binomial expansion and a generalization in fulfillment of the extra credit video assignment for Math 2030 for the semester Fall 2020. First, what we're going to do is motivate our study with something that's familiar to all of us. We'll take an arbitrary binomial, x plus a, and we'll square it. So we are taught if we want to expand this, we use a method called FOIL, which stands for first, outside, inside, and last. So this is just a rule for expanding it out. So we'll demonstrate it here quickly. X plus a squared is x plus a times x plus a. First, what we do is we multiply the first two terms, the f, x times x, the outside terms, x times a, the inside terms, a times x, and the last two terms, a times a. And then we can simplify this. We get x squared plus 2ax plus a squared. This is nice, and it is a really easy way to expand a binomial to the power of 2, and we use it all the time in classes such as pre-calculus and basic algebra and calculus. But what happens if we have a binomial that's to a higher power than 2? We start to run into some issues. So, for example, let's look at x plus a to the power of 3. This is equal to x plus a squared times x plus a. We see from here we have 3 terms. So we're going to have a 3-term expression multiplying by a 2-term expression, and our FOIL method doesn't work. Now, we could use distributivity and still come up with the right answer, but this is going to become unwieldy for higher powers than even 3. So if we go to 30, just think about how much work you're going to have to do to get a fully simplified expression. So we need a better way to do this. This is not going to work. So luckily for us, from our study of combinatorics, we can figure out a formula for general binomials to an arbitrary power, say n. Okay, so returning to our example of x plus a squared, what we saw is we have x times x plus x times a plus a times x plus a times a. This is really important, and it's a subtlety that gets lost as generally we simplify the expression in our head and just write down what we have at the bottom here. But what this looks like is if we had a set x and a, and we wanted to write out a list of all possible combinations of 2 elements from this set, with repetition, of course. So we could choose an x and then an x. We have that over here. We could choose an x and an a, or an a and an x. We got both those. Or we could choose 2 a's. In fact, the coefficients of our last expression were telling us how many ways we could pick elements from the set. So we could have chose an x and an x. There's one way to do that. We could choose x and a, or a and x. That's 2 ways. Or we could choose a and a. That's 1 way. We can take this a step further. Using this combinatorial framework, we can apply this to arbitrary power n. So if we write this out, we get x plus a times x plus a, all the way to x plus a, n times. Again, we are looking at all the possible orderings of x's and a's of length n. Let's fix x. In the next term, we can choose an x or an a. And we can view this as if we are multiplying. We can multiply it by an x, or we can multiply by an a. We can keep this process going for each term, for each of the n terms, and what we'll end up with is out of all of our n binomials, k of those binomials are going to be ones where we chose an x. And k is some number between 0 and n inclusive. So using our combination notation, we'll have n choose k, x's. But when we think about it from our list, we can multiply those x's together, and there's k of them. So we take x to the power of k. How about how many a's did we choose? So we need to figure out what number plus k is equal to n. In fact, there's only one option for this. It's n minus k, since k plus n minus k is equal to n. So this is our expression, and we can do this for any k between 0 and n like we said. So by the rule of sum, what we're really doing is we're summing over all k's from 0 to n. And this is our final expression. This is our binomial expansion. In fact, we have just outlined a proof for a formula of x plus a all to the power of n. Okay, let's do an exercise from Roberts and Tessman's Applied Combinatorics to get a more concrete idea of what we're dealing with. What we want to do is find the coefficient of x to the power 11 in the expansion of 2 plus x to the power of 14. Now, recall our formula was x plus a to the power of n is equal to the sum from k equals 0 all the way to n, and choose k, x to the power of k, a to the power of n minus k. Okay, so what we're going to do to solve this is we're going to plug this into the formula. So we'll get 2 plus x, power 14. Now this is equal to the sum from k equals 0, now up to 14. Of 14, we're choosing k2's, and then we will be choosing 14 minus k x's. So our goal is to find the coefficient of x to the power of 11, and we get that when k is equal to 3 because 14 minus 3 is equal to 11. So let's plug in k equals 3 and see what we get. We'll have 14, choose 3, times 2 to the power of 3 times x, 14 minus 3. And this will give us our coefficient, 8 times 14, choose 3, of x to 11, as desired. And that's our final answer. All right, now we're going to walk through what is Theorem 2.8 from this textbook, but we will try to derive it a bit more naturally. What if we wanted to know how many subsets of an n set there are? So we have an n set. How many different subsets could we make from this? So using our combinations, we know that we could have n, we could choose 0 elements. That's a set. In fact, that's the empty set. Using the rule of sum, we could have also started with our n elements and chose 1. Again, n, we could choose 2. And we could continue this all the way up, n, choose n, which would give us our original n set. Now, how are we going to connect this to our binomial theorem that we had previously? So we want to form this into our summed expression from before, but we can't change any of our binomial coefficients. And the only way we could do this is n choose 0 times 1, that doesn't change it, times 1 again, and we can raise 1 to any power we like, and it will still be 1. So why don't we say the power 0 and then the power n. And now what we're doing here is we're just following the formula. That's where we're getting this idea from. So now when we have n choose 1, we have 1. We can do the power 1 times 1 to the power n minus 1, and so on, all the way up to n choose n, where we have 1 times n times 1 to the power 0. These are equal. And if we condense this notation, what we've really just done here is we have a sum from k equals 0 all the way up to n of n choose k, coming from these guys, 1 to the power of k times 1 to the power of n minus k. And if we connect that to our binomial theorem, we know, using these two ones here, this is equal to 1 plus 1 to the power n, which gives us 2 to the power n. So that tells us how many possible subsets we could have of an n set. And we can see in this small example how powerful the binomial theorem really is, because this seems like a hard problem to solve if we have an arbitrary number of elements in our set. There's many possibilities we could have for subsets, and now we've condensed it into something we can work with. Taking our thinking from before, we can in fact generalize our binomial expansion to multinomials. So we want something that will work for multinomials of the form x plus 1 plus x plus 2 all the way to x plus m to the power of n. Okay? Again, we are determining every possible ordering of our set x1 through xm that has n elements. Okay? Let's write this out as we did before. So we have x1 plus x2 plus dot 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 to xm. And we'll write it out as if we are multiplying it out. Okay. So again, we have n terms here. And now let's focus on x1. We're going to do the same thing. When we multiply it out, we have m choices that we can have to multiply it with. X1, x2, all the way up to xm for everything in our expansion of n multinomials. Let's denote the number of x1s we choose by k1. So we'll have n. We're going to choose k1, x1s, the power of k1. Now we'll denote how many x2s we choose by k2. Now we can make use of our multinomial coefficients from previously in the course, and we know that we get n choose k1, k2 times x2 k to the power 2. And we can continue this all the way up to x to the x sub m. And in fact, we get this multinomial coefficient of n choose k1 all the way through km. And for each x in our list, we'll have it to the corresponding power. For each xi, we'll have it to a corresponding power xki. And what we want to notice here again is that our list of x1s through xm's can only have n elements in it. So what we need is we need k1 plus k2 plus km to all sum to n. Okay? So what we're really doing here is we have k1 all combinations of k1, k2, in essence, all solutions to the equation k1 plus k2 all the way to km equal to n. We'll write down our binomial coefficient from before, or we'll write down our multinomial coefficient from before, I should say. Times x1 to the power k1, x2 to the power k2, all the way to xm to the power km. This, in fact, will be our generalized formula for multinomials to an arbitrary power. So what we're looking at here is every possible, or every non-negative solution for non-negative k1 through km, all summing to equal n. And in fact, if we wanted to know how many terms we had in our expansion here, we know how to solve this problem from earlier in the course. Essentially, we have k1 plus k2 up to k1 equal to n, where ki is greater to 0 for all I equal to 1 up to m. And we had previously found in the course how we solve this. In fact, it is equal to the combination of n plus m minus 1, choose m minus 1. So this is the number of terms we will have in any multinomial expansion we do. Okay, now we're going to look at some problems from the textbook that will hopefully be a little bit easier for us to get a handle on and shed some light as to what's actually going on when we're expanding the multinomials. Okay, so let's say we want to find the coefficient of x, y squared, z squared, w in x plus y plus z plus 2w to the sixth. Okay, so what we're going to do, as we did for a similar example for binomial expansions, is we're going to plug this into our formula we found for the multinomial expansion. Okay, so we have x plus y plus z plus 2w to the 6 is equal to the sum. Now we're going to use k1 through k4 since there are 4 terms. So we have 4 powers to worry about. k1 plus k2 plus k3 plus k4, summing to 6. So all non-negative solutions to this equation. And we have the multinomial coefficient 6, choose k1, k2, k3, k4. And we'll have x to the power k1 chosen. Same for y, k2, z to the power k3, and 2w all to the power of k4. Okay, so what we have in the question is x times y squared times z squared times w. And we can think these are just ones up here for the powers of x and w. So k1 is equal to 1, k2 is equal to 2, k3 is equal to 2, and k4 is equal to 1. And we should see here that k1 plus k2 plus k3 plus k4 is in fact equal to 6. Now this is really important. We need it to be 6 for it to be in our expansion, and in fact it is. So we know that this term does exist in the expansion, and now we can just plug in the numbers to find the coefficient. Okay, so we'll have 6 choose 1, 2, 2, and 1, and we'll have x to the power of 1, y to the power of 2, z to the power of 2, and 2w all to the power of 1. Okay. Now what we'll see here is this will evaluate. We'll have 6 factorial over 2 factorial, 2 factorial. We can ignore the ones. We'll have x, y squared, z squared, and then 2w. And in fact, the coefficient, the 2 here and the 2 here, the 2 factorial will cancel. So our coefficient for the term will be 6 factorial over 2 factorial. And that's our final answer. Okay, so we're going to wrap this video up by modifying an example from the textbook to illustrate an important point about finding coefficients of terms in the multinomial expansion. Okay, so we want to find the coefficient of a cubed, b squared, c squared, d to the 6 in this guy right here. Okay, we're going to do the same thing we did before. We have our solution. We'll have a plus 5b plus 2c plus 2d to the 12. Using our formula, we'll have the sum of, we have 4 terms, so we're going to have 4 k's, k1 plus k2 plus k3 plus k4, summing to 12. We'll have our multinomial coefficient here, 12. Choose k1, k2, k3, and k4. And multiplied by a, we're choosing k1 of those. 5b, we're choosing k2. 2c, we're choosing k3. And 2d, we're choosing k4. Okay, so in the question, we are given k1, k2, k3, and k4 in this expression here. So k1 is equal to 3, k2 is equal to 2, k3 is equal to 2, and k4 is equal to 6. Here's the really important part. We notice that if we sum all of these together, we get 13. This is not 12. What that is telling us now is that this term does not appear in our multinomial expansion. So in fact, there is no coefficient of a cubed, b squared, c squared, d6 in our expansion. Okay, that's going to do it for me today. Thank you for watching and stay safe.